Hello, my name is Vigneshwaran Analaki Kumar, matrix number U2003979/1. This is the group presentation for the subject KIG 2001 Fundamentals to Electrical Engineering. The topic of our choice is smart home lighting and fan. These are the group members of this group assignment along with their contributions to the reports, the slides, and the calculations. Let me start off by the introduction of our assignment. We have chosen an automated lighting and fan system that is actually temperature dependent. Hence, our system switches on the fan and lights when the temperature of the room exceeds a certain threshold temperature, and it is turned off when the temperature is below that certain threshold temperature. You might be wondering, why did we choose this specific title for our project? Well, we did this to address a few problems. The first problem is that energy sometimes is wasted when lights and fans are turned on manually. For instance, sometimes the lights and fans at our home are not switched off when it is not necessary. It might be due to negligence, and our automated lighting and fan system will address this issue. Secondly, we would also like to address the fact that sometimes lighting and fan systems are operated at higher modes than its actual requirements. For instance, the fan at our home might be actually running at a much higher speed than it is required. Moving on, based on the problem statements previously, we have set certain objectives to address these problems. Firstly, is to design a circuit that is controlled by the temperature of the room. Secondly, the objective is to integrate the temperature control circuit in home lighting and fan systems. Thirdly, our objective is to analyze and verify the electrical circuit elements based on manual calculations as well as the MATLAB simulations.
Hi, my name is Daniel Hozion with metric number U2003933. This is the design circuit from our group. The main purpose is that the bulb and motor will automatically switch on at low temperature and switch off at high temperature. This circuit consists of a 9-volt voltage source to supply voltage, two resistors with 5000 ohm and 100 ohm respectively, which act as voltage divider. One thermistor which is responsible for changing its resistance according to the temperature, one NPN bipolar transistor, 100 ohm light bulb, and also a DC motor. The voltage sensor and current sensor are also connected as shown in the picture to test the voltage across the bulb and the current flow through the branch. The value is shown as in the picture. Basically, when temperature is low, the resistance of the thermistor will be high and the current will flow through the collector branch, causing the motor and warning light to operate. In the case of high temperature, it is vice versa. We can see that at high temperature, the value for bulb voltage and current flow through it is very low, which can be assumed as zero, and therefore it stops operating. Based on these two graphs, we can see that the torque is higher at low temperature than at high temperature because the current at low temperature is higher. Therefore, the higher the current, the greater the torque will be. Besides, the current and voltage against time graph for each high and low temperature cases are also shown in this PowerPoint.
Next, we are going to validate the value that's shown at the sensor for temperature of 273.15 Kelvin. Firstly, we need to find the resistance at the thermistor. It can be calculated by using the formula as shown in the slides. So we refer the formula from the datasheet of the thermistor. So we plug in the value into the formula and we will get 1000 ohm for resistance of thermistor. Then we need to determine the total impedance by using the formula as shown in the slides. So we plug in the value into the formula and we will get 197.20 ohm for the total impedance. After that, we can find the total voltage and current in each branch. As in the slides, we apply Kirchhoff's voltage law, KVL. At branch 1, we get 9 volt for the voltage and 0.0015 ampere for the current. At branch 2, we get 9 volt for the voltage and 0.04412 ampere for the current. So the calculations are very approximate to the exact value as shown at the current and voltage sensor. So it proves that there are current flow in the circuit when it is at low temperature place. So we assume that we do not get the exact value because we disregard the calculation at the transistor as the value is very small and maybe it detects the leakage current that occurs in the circuit. We move on to the total voltage and current. The total voltage is equivalent to the voltage source, which is 9 volts, and by using the Ohm's law, which is V is equals to IR, it can be calculated as follows. So the total voltage would be 9 volts, and the total current we get 0.04564 ampere. And then for the power input, we take 9 volt as V input and current input as 0.04564 ampere, which is the same as the total current value. So we will get 0.41076 watts. For power output, we take V out as V motor and the current value of 0.04414 ampere. So we will get 0.007599 watts.
Hi, I'm Satish Rao. Matrix number U2003873/1.
For the scenario of high temperature, we can see from the circuit that the current source indicated the current sensor is 7.389 times 10 to the power of negative 9 ampere, which is also 7.389 nanoampere when the temperature is 303.15 Kelvin. This shows that at the branch that contains the warning light, the current flow is very low or can be assumed as no current flow at all. With the nature of thermistor where its resistance vary due to temperature, we can see that at temperature 303.15 Kelvin, the resistance of thermistor is only 78.17 ohms. This calculation is validated in slide 21. This is very low when compared to the scenario of low temperature, where the resistance of thermistor is 1000 ohms. From the application deduced, we want the lights to turn on during a cold temperature while the lights should be off at high temperature. In addition, due to very low value of current, the values obtained such as power output of motor, voltage and current at branch can be ignored since the circuit is no longer usable. This can be further proved from the graph generated in MATLAB in slide 8, 10 and 11. We can see that when the temperature is 303.15 Kelvin, the value of torque, current and voltage remains at 0. Although in the circuit diagram shows a value, but in reality any value with the power of negative 9 is very low. Therefore, validation of calculation is only done for low temperature scenario because the circuit is usable and easier to be interpreted.
Hello, I'm Jiyun Raj, matrix number U2003950/1. I will be explaining for the argument of our extended circuit. So our circuit application can be used in the street light, incubator, and also the aircon. The street light will light up automatically when the temperature is low, especially at night, where compared to daytime, at night the temperature is lower. And when it reaches daytime, the temperature of surrounding which exceed the specifically required temperature will cause the light to turn off. When the temperature is low, the circuit can trigger the aircon to activate, and after a specific area reach certain required temperature, the aircon will deactivate automatically. For small individual entrepreneurs, the incubator will come in handy as the circuit will light up when temperature is low and turn off automatically when it reaches the threshold temperature. So the individual just need to state what temperature is the max and it will turn off automatically when it reaches it. So in conclusion, we have demonstrated successfully that the electrical design that we designed will perform and function well, and it fits in our smart home lighting and fan. With the presence of thermistor, the electrical circuit can automatically light up when the temperature is low and turn off when it reaches the threshold temperature. A smart alarm system can be installed in our daily use gadgets such as our mobile phone to inform us in case of any malfunction. We have also included the reference sources in the reference section. Thank you.